Counter-sniper story, the limitations of technology. During John Muhammad's and Lee Malvo's October 2002 sniping spree in the Washington, D.C. area, law enforcement officials attempted to use counter-sniper technology to find the two killers. More specifically, police tried to use the Viper muzzle flash detection and location system employed from both a helicopter and an airship to find the shooters. The overall experience revealed some of the limitations of current counter-sniper technology. The Viper system consisted of a mid-wave infrared camera intended to pick up the muzzle flash of a weapon. Once the IR camera detected a muzzle flash, it cued a visible light camera and then focused on and recorded the area where the muzzle flash was detected. When the Viper detection system was tested from a helicopter at the Fort Meade, Maryland rifle range, it reliably detected muzzle flashes down below. However, this was unrealistic testing as the DC snipers were firing in dense urban areas while the rifle range was open rural terrain. The Viper system was fundamentally flawed because it was based solely on detecting the muzzle flash of a weapon. To be fair, the Viper's IR system was equipped with various filters to limit the number of false alarms and to distinguish a true muzzle flash from other infrared clutter. The problem was the DC snipers fired the majority of their shots from the trunk of their car, so there was no visible muzzle flash. So if the Viper system was deployed in a manner where it could operate within its capabilities, Viper would have detected absolutely nothing. In this case, the street-savvy tactics of the two shooters outwitted millions of dollars of technology and machinery. Because the visible camera on the Viper was cued by the detection of a muzzle flash, this part of the system was also eliminated as a useful tool. It would have been great if the visible light camera set up to automatically point towards an identified muzzle flash filmed the shooters in the act of or as they tried to get away. This footage could be used in court as evidence to prosecute the killers. However, since there were no muzzle flashes, there would be no infrared detection and there would be no visible light recording the events. With the Viper, one flawed system was tied to the other, rendering both of them useless. Part of the difficulty of employing the Viper system was finding the right platform for it. Using the system in a ground configuration was quickly ruled out because the area to be covered was huge, an area roughly from Frederick, Maryland to Baltimore, Maryland to Richmond, Virginia. For the Viper to work, the operators needed the exact location of the shooters and they had to be within line of sight of their muzzle flash. Since the shooters struck at random with no predictable pattern, a ground-based strategy had 0% chance of success. Consequently, the Viper operators decided to cover a much larger area, and to guarantee a better chance for line-of-sight detection of a sniper's muzzle flash, they set up the Viper system in a Jet Ranger helicopter. To accommodate the system, they left the door of the Jet Ranger removed, and the Viper, powered by 2 car batteries, was ready to go. Testing the Viper Jet Ranger system revealed that flying below 100 feet caused an unacceptable number of false alarms due to random objects being blown around from the rotor wash. However, FAA restrictions mandated the Jet Ranger fly at or above 1,000 feet. At that height, during testing, muzzle flashes were reliably detected. While helicopter operations were feasible, the Jet Ranger suffered from relatively short air endurance and had to return frequently to base to refuel. Therefore, it was decided to mount the Viper system on a U.S. Navy-leased Airship 600. The airship had several advantages, such as its relatively low speed and long air endurance. On the other hand, operating the airship out of the relatively limited Washington, D.C. temporary flight restricting area was a challenge. In the end, the aerial Viper system was never employed because the DC snipers were caught the day before the airship was finally ready to be used. Another attempt at sniper detection, the RC-7. As the DC snipers continued to spread terror despite a massive police presence, a decision was made to employ military assets to try and detect the shooters. Secretary of Defense Don Rumsfeld authorized the military to use their RC-7 Airborne Reconnaissance Low Aircraft, ARL. There were some legal concerns using the military's RC-7 to help in a domestic criminal case because of possible violation of the 1878 Posse Comitatus Act, which prevents the U.S. military from performing civilian law enforcement. The military got around the law by agreeing the military personnel operating the plane would only work the surveillance equipment and the police would conduct the analysis and investigative follow-up. Defense officials thought the RC-7 could help with the sniper problem because of its sophisticated infrared sensors that could perform surveillance of large areas, both day and night, and then transmit what its cameras saw to operators on the ground. The military even considered using Predator unmanned aerial vehicles, UAV, and NAW-P3 Orion surveillance planes to help in the search, but because they were in such heavy use against the Taliban in Afghanistan, the option was canceled. What exactly were the capabilities of this plane which was supposed to succeed where Earth-based law enforcement failed? GlobalSecurity.org describes the plane's capabilities in depth. The Airborne Reconnaissance LOW, ARL, is a multifunction day and night all-weather reconnaissance intelligence asset developed and fielded by the Army in support of an urgent requirement for a low-profile intelligence aircraft. It consists of a modified DHC-7 fixed-wing aircraft equipped with communications intelligence, COMINT, imagery intelligence, MINT, and moving target indicator, synthetic aperture radar, MTI, SAR, mission payloads. The payloads are controlled and operated via onboard open architecture, multifunction workstations. Intelligence collected on the ARL can be analyzed and recorded on the aircraft workstations in real time or stored on board for post-mission processing. During multi-aircraft missions, data can be shared between cooperating aircraft via ultra-high frequency, UHF, air-to-air data link to allow multi-platform COMINT geolocation operations. The ARL system includes a variety of communication subsystems to support near real-time dissemination of intelligence and dynamic retasking of the aircraft. The ARL system was developed to accommodate diverse mission requirements through the implementation of an open architecture, modular, reconfigurable mission sensors. These systems can be operated separately or can be used to cue each other for examining targets using different sectors of the electromagnetic spectrum. The systems are controlled from 4 workstations within the aircraft by the mission analysts. The de Havilland of Canada-7, a 4-engine turboprop commuter plane, was chosen as the platform for SIGINT and MINT collection. The -7 aircraft's ability to operate out of austere runways, its ability to carry the mission payload, and its endurance led the -7 selection. It is an extensively modified aircraft that has a higher maximum gross weight and extended range capability added in the ARL conversions. The -7 is a medium-sized 4-engine passenger and cargo transport. It is pressurized and can operate at up to 20,400 feet with a full mission crew. Mission duration can be up to 8 hours with a range of 1,400 nautical miles at a cruising speed of 230 knots. Proposed future engines and wet-wing fuel tanks may extend the range to 2,800 nautical miles. The cockpit has been upgraded to Aerospace 2000 standards. The system developed from a Commander-in-Chief U.S. Southern Command, SOUTHCOM, requirement for a manned aviation platform that could provide an MINT and SIGINT collection capability in SOUTHCOM. The design requirements submitted stated that airborne reconnaissance LOW should support nation-building, counter-narcotics, and promote democracy missions, now classified as stability and support operations or operations other than war, in SOUTHCOM's area of responsibility. The RC-7s were initially deployed with U.S. Southern Command, SOUTHCOM, in 1993 to assist in counter-drug surveillance operations, and later deployed to Haiti in support of U.S. peacekeeping operations. In 1996, an RC-7 was deployed to Bosnia-Herzegovina to support NATO's I-4 peacekeeping force. So, how did this all-weather 10 million-plus superplane perform as a counter-sniper system? The RC-7 never did detect the snipers in the act, This is because the RC-7 suffered from the same limitations as the Viper system. The RC-7 relied primarily on IR imaging to detect the muzzle blast from a weapon and therefore had no better chance of detecting the needle in the haystack than did the Viper. And the fact the RC-7 had powerful cameras capable of reading a license plate from its orbit and then transmitting this detailed imagery to users on the ground also was of no use. If the RC-7 did not know where to look and point its sensors, then it was out of luck. Again, because the DC snipers fired a single shot at random throughout a large geographic area made up of a dense urban environment, the military's multi-million-dollar surveillance plane, which worked great in the open waters against drug runners and cigarette boats, was useless against a lone shooter firing from the trunk of an old beat-up Caprice Classic. Into the future. We are truly in the computer age, and the trend towards technical means of counter-sniper detection is not going to fade away. Quite the opposite is true. We can expect a growth in counter-sniper technology as it becomes more reliable, accurate, and rugged. Someday, every soldier or police officer may be a counter-sniper system, each armed with a small, handheld, or vehicle-mounted device able to detect a gunshot through a variety of means such as acoustic, radar, and thermal imaging. As of the writing of this book, the trained, educated sniper still holds the edge over the counter-sniper machines when working in the complex urban environment. Someday, one can expect more sophisticated counter-sniper machines will eventually take the edge away from the sniper, and the lone shooter, no matter how skilled they are, will be at a disadvantage. However, all is not lost for the sniper. The sniper will not be wiped out by the machines if they adapt to their new environment. What kind of adaptations are we talking about? Are we talking about better camouflage, better rifles, exploiting the urban terrain more cleverly? No. For the modern sniper to adapt into the future, they must accept the fact technology is growing, and it must be embraced, not avoided. In turn, the sniper can also use technology to their advantage. Use a machine to defeat a machine. The following chapter will explore how snipers can exploit modern technology to defeat the growing threat from counter-sniping technology.